We're going to now talk about a class of integrals called improper integrals. And these, we'll see there are two different types of improper integrals that we'll talk about, and they have to do with things that are happening at infinity. So I want to look at two graphs that are fairly similar. First, this guy and this function here. This first function is a familiar one. It's f of x equals 1 over x. And the second function is pretty close relative, 1 over x squared. And these are, we're going to look at the area. We're really interested in being able to calculate the area from x equals 1 all the way to, we'll accumulate all this area, all the way out to infinity, actually. So it just keeps on going. And similar for the other guy, we're going to look at the area between the curve and the x-axis from x equals 1 all the way out to infinity. And so these functions are going on and on and on, both of them to the right. They actually never touch the x-axis. They get closer and closer and closer as they go, the x values get larger and larger. But these functions, even though they get closer and closer, they never touch the x-axis, no matter how far out you go. And so the question that arises is an area that is unbounded, it keeps on going and going and going. Is it possible for such an area to be finite, even though the area itself is unbounded? It's an unbounded region, but can it have a finite area? And the answer is sometimes. This guy right here, this pink area, the area is actually infinite. It keeps on growing and growing and growing. And this guy here, if we summed it up all the way from 1 out to infinity, all of that area between the curve and the x-axis will be finite. It's equal to 1. We say that counting up the area, in this case, that area, it would diverge. But the area from 1 to infinity, in this guy, it converges. It converges to a finite number. So these guys are so similar. What is it that makes them different? Why doesn't this one converge, or why doesn't this one diverge? And that's what we're going to look at. This is the first type of improper integral. So both of these are examples of improper integrals. It basically just means that one of our endpoints on our integral is going to be infinity. So the left one, that 1 over x function, we would write the integral from 1 to infinity. This is the first time that we ever see infinity as a limit of integration of 1 over x dx. And the one on the right we would write as the integral from 1 to infinity of 1 over x squared dx. I will tell you that this one on the right is equal to 1. That all of this area, if you sum it up, even though it goes on infinitely long, will equal 1. And the one on the left, I'll tell you, it diverges. And so there is no number that this limit approaches. It will always just get up to be a bigger and bigger and bigger area forever. So this is describing this picture, and this is describing this picture up here. So for the first time, we learned that it is possible for the area of an unbounded region to be finite. That's a pretty cool idea. We haven't seen this before. So why do we even care about improper integrals? Some of the applications, they're actually used in a variety of ways. In probability and statistics is probably the most frequently, where they're most frequently used. Probability, you'll see improper integrals in what are called probability density functions. And then also in physics, density functions. In physics, there's some applications with electrostatics. And these are not even close to all of the ways that improper integrals come up, but these are a couple of the most common. So let's talk for a minute about why these two examples are so different. If we're interested in calculating the integral from 1 to infinity of 1 over x dx, technically we're going to write this as a limit. We can't really plug in infinity into an algebraic expression and evaluate it. So we're going to put a kind of a dummy variable called t, and we're looking at the limit as t goes to infinity. So, at first t could be right there, and then it's moving out and out and out to infinity. So the limit as t goes to infinity of this integral from 1 to t of our function. And this will equal to the limit as t goes to infinity of the natural log of x evaluated from 1 to t. This is the limit as t goes to infinity of the natural log of t. We could probably drop off the absolute values because t is always a positive number, minus the natural log of 1. Natural log of 1 just goes to 0. So we're looking at the natural log of t as t goes to infinity. And you probably remember what the natural log curve looks like, that it's a curve like this, but it's a curve that keeps growing and growing. Even though it's growing slower and more slowly, it does keep forever after going up and up and up. So this expression here will never converge to a number. It's always growing. And so this is, in fact, why we say that this integral diverges. It has to deal with the fact that the natural log curve keeps growing. And what we ended up with after we integrated was essentially the natural log as t goes out to infinity. So after we integrated, we ended up with this function that just keeps growing. Let's see what's different about the function 1 over x squared. Okay, so here we're also looking for the integral from 1 to infinity, but this time it's of the function 1 over x squared dx. And we're actually going to take the limit as from 1 to t as t approaches infinity. And so integrating this is not really a problem. We know that the integral of this is just negative x to the negative 1, or the antiderivative. And so this equals the limit as t goes to infinity of negative x to the negative 1 from 1 to t. And so this I just got because I know that if I take the derivative of this, I will get 1 over x squared. So this is a proper antiderivative. Okay, let's plug in the t and see what happens. This will equal the limit as t goes to infinity of negative t to the negative 1 minus negative 1 to the negative 1. Okay, 1 to any power is just 1. And then we have a negative negative, so we're going to be adding a 1 here. And this is like a negative 1 over t. And it's still the limit as t goes to infinity. Okay, so now we have a different situation. Now we have, as t goes to infinity, this expression here will get smaller and smaller and smaller, and it actually goes to 0. So the limit as t goes to infinity of this first part is 0. And then this is not dependent on t at all. It just stays 1 no matter what's going on with t. So the result of the whole limit is the number 1. And this represents this integral. So this is the area under the curve from 1 to infinity. And this is an improper integral that converges to a finite number. So we've just seen a couple examples of improper integrals of the first type. And this is whenever one of your limits of integration is infinity. So it could look like this. It could look like maybe you're going from negative infinity to some number. Or a third possibility is you're going from negative infinity to infinity of your function. And there is one little thing we need to mention, that we do have to assume that the integral from a to t will exist for any number t that's bigger than a in this case. So this is just an assumption that we make. Otherwise, you can't take the limit as t is going to infinity if for one of those t's the integral doesn't exist. And it's similar for this case. The notation would be slightly different, but the idea is all of those integrals that we're traveling by as t is going to infinity or negative infinity have to exist, have to be there. Then we say that the integral from a to infinity of f of x is equal to the limit as t goes to infinity of a to t f of x dx. This is what we did in the last example. And so this applies to this, but it's going to be similar for these guys. Okay, this is what it means to have infinity as a limit of integration. And then we have our two cases. Either it's going to diverge or it's going to converge. And so these two cases, these are essentially the questions that you're going to be asked about improper integrals. Is you're going to be thrown in, it'll look like this. You'll be thrown an improper integral and you'll be asked, does this diverge or does it converge? And if it does converge, what does it converge to? Let's pause here, and I just want to write a little note about those first two examples because they're a fairly common example. So we had 1 over x, and then we had 1 over x squared. You could have 1 over x to the third. You could have almost any power in x. So say that we had 1 over x to the p. This integral from 1 to infinity. So this is, kind of one of the building blocks of improper integrals is to talk about this particular pattern here. Well, we saw that when this p was 1, that it diverged, and when it was 2, it converged. So is there kind of a pattern that we could always tell just based on this power what if it will diverge and converge? And yes, there is. If this power here is between 0 and 1, it will always diverge. So it diverges for all the p between 0 and 1, including 1, and it will converge if p is greater than 1. We saw that when p was equal to 2, it converged. So, you could have like the integral from 1 to infinity of 1 over x to the 2.3, and we know that that will converge. It's just a pattern. Or if it was x to the 7th, we know that this will converge. Conversely, if you had 1 to infinity, the integral of 1 to infinity of 1 over x to the maybe 0.5, This is something that will diverge. You'll never be able to say that that integral equals a finite sum, or if it was equal to like 0.1, that these will always be divergent. And that's just a good pattern to remember. It's an easy one to remember. Just between 0 and 1, this power, this will always diverge. And then if you get a power larger than 1, this will always converge. Okay, so let's look at another example. We're going to take the integral from 1 to infinity of 1 over square root of x dx. And I don't even need to evaluate this one really, because this falls into the case that we just looked at. This is 1 over a power of x. This is x to the 1/2. And so, 1/2 is between 1/2 is less than or equal to 1, and it's greater than 0. So just based on that and the pattern that we just talked about, this integral has to diverge. So that's nice. We don't even have to go through the work of evaluating it. But let's look at another example that's a little more in depth. Let's say that we want to find the integral of, and this time we're going to go from negative infinity to infinity. This brings up some new ideas also of x e to the negative x squared dx. Okay, so this is a little bit more interesting, this function right here. And then we're also going from negative infinity to infinity. When you go from negative infinity to infinity, you actually treat it as two separate improper integrals. So we're going to go from negative infinity to 0. That's the first half. And then to that, we're going to add from 0 to infinity of the same function. And of course, we're going to say, well, we can't evaluate algebraic expressions by plugging infinity in. So let's say that this is equal to the limit as t goes to negative infinity. So this is the limit as t goes to negative infinity of this expression. And same story over here. Let's take the infinity out and put this variable t in. And we'll look at the limit as t goes to infinity. Let's take a look at this one first, just because I like not dealing with negatives. And so if we were going to evaluate this integral, the antiderivative of this, we could pretty quickly find, like with a u substitution, u equals negative x squared, then du equals negative 2x dx. And so really we're looking at the negative 1/2 integral of e to the u du. I don't want to change my limits of integration, so I'm going to look at what this will be and then really go back into my original limits and my original variables. So this will be, this integral here will be negative 1/2, keeping our limit as t goes to infinity of negative 1/2. The integral of e to the u is just e to the u, so that's e to the negative x squared. And we're evaluating it from 0 to t. This equals the limit as t goes to infinity of negative 1/2 of, let's see, e to the negative t squared minus a negative 1/2 e to the 0. And this equals, let's think, this right here, well, e to the 0 is just 1, so this becomes a positive 1/2. Because that's just equal to 1. Now this expression here, e to the negative t squared, this is like a 1 over e to the t squared. T is getting bigger and bigger and bigger, so this number will be getting bigger and bigger and bigger, so this all is going to 0. So this expression, as t gets larger, is going to go to 0. And so we have 0 plus 1/2. We don't need the limit anymore. So this part of the integral actually does converge to the number 1/2. So from 0 to infinity, the area under this curve is 1/2. Let's go and do this part now. And so this will be the limit as t goes to negative infinity. We'll go ahead and just kind of coast off of this differentiation, and we know that this is negative 1/2 e to the negative x squared, this time from t to 0. And this is the limit as t goes to negative infinity. Okay, so we can start plugging things in. Negative 1/2 times e to the 0, that's 1, minus negative 1/2 e to the negative t squared. And so we want to take a minute and figure out what's going on with this, knowing that t is getting bigger and bigger as a negative number. Is this turning positive? No, it's not, because that negative large number t is going to be squared first, and when it's squared, it turns positive. And so we have still a negative large number here. And so just like what happened here, e to a negative large number goes to 0, and we have, so that goes to 0. And we've got negative 1/2. This 1/2 was, or negative 1/2 was not dependent on t at all, so it just stays as it is. So we have negative 1/2 for this part. Okay, so we have the first part of the integral equals negative 1/2. The second part equals 1/2. So this whole integral here actually equals 0. The left half cancels out the right half. So this equals negative 1/2 plus 1/2 equals 0. Let's get a picture of what's going on just so we can understand why this is 0. So this is a picture of the function f of x equals x times e to the negative x squared, and we can see why this integral was equal to 0. We have a bunch of negative area here and a bunch of positive area here that's symmetric. This function never touches the x-axis, either to the right or to the left, but even though that area is unbounded, it's a finite, it converges to a finite number. So this is where we see that from negative infinity to 0, our function was equal to negative 1/2. That was just all this area in here, negative 1/2, and it keeps on going. And then all of this area over here was a positive 1/2. So here from 0 to infinity, the function was a positive 1/2. But it would be totally legal also to say, okay, well, what's the area from 1 to infinity? That won't be 0 and it won't be 1/2. It'll be a number less than 1/2. But so you could be asked, a question like, what's the integral from 1 to infinity of x e to the negative x squared dx? And we would do similar work to come up with this positive number that's less than 1/2. Let's look at another example of this type 1 improper integral that shows something a little bit new. We are going to go from negative 2 to infinity of sine x dx. So this is this definitely is an improper integral because one of our bounds is infinity, and we can do the work. We can say, okay, this is just the limit as t goes to infinity of negative 2 to the t sine x dx. This is the limit as t goes to infinity of negative cosine of x evaluated from negative 2 to t. And this equals the limit as t goes to infinity of negative cosine of t minus negative, so a plus cosine of negative 2. And so we've done the integration, we've evaluated at the endpoints, and we have to think about what's happening. This is just a constant. It doesn't depend on t at all. It just is what it is. But as t goes to infinity, what is happening to this guy? Well, the cosine curve, or the negative cosine curve, looks something like this. It just keeps oscillating up and down and up and down. And so because of that oscillation, this part of it, as t goes out to infinity, will never converge onto a single number. So this whole thing will never converge. The limit doesn't exist. And so we say that this is divergent. So the limit doesn't exist. That cosine keeps oscillating. So as t goes to infinity, it never lands on one number or converges to one number. So this is divergent. So we look at this guy who is divergent. This guy was convergent. You can sometimes tell, but you can't always tell which is going to end up being convergent and which is going to end up being divergent. We're going to look at improper integrals, the second type. What we just looked at was where we were going on forever horizontally. That was the first type of improper integrals, going off to, x was going off to infinity or negative infinity, and so we got that one. Now we're going to look at improper integrals where you're going on forever vertically. So you have some kind of vertical asymptote, and this is the second type. These are slightly more subtle because you can't always tell when you're looking at an integral that you might have a vertical asymptote right smack dab in the middle of it. So the first example I want to look at is this one. We're going to go from negative 1 to 2. So here, this will end up being an improper integral, but it's not the limits of integration aren't infinite. Something's happening inside here in the integrand that is causing a vertical asymptote that we have to watch out for and kind of work around. So x to the negative 4/3 dx. This is what we want to evaluate. This is an improper integral, though we might not notice it at the beginning. But think about where we're going from negative 1 to 2. And this is essentially like a 1 over x to the 4/3. And between negative 1 and 2, we hit the number 0. If we tried to evaluate this function at 0, that would be a major problem. And so that's what's causing a vertical asymptote. But let's just forge on and see how we handle this. So we're going to say this is equal to negative 1 to 2 of this guy, just so we know, oh yeah, x equals 0 is a problem. And if I graphed this function, this integrand, I would get something, say -1 is here and 2 is here. This function looks something like this. And what we're asking for is this area between -1 and 2. But smack dab in the middle of it is this vertical asymptote where things are going on up to, the value of the function is going up to infinity. And so we're kind of asking, can we even calculate this area? Because it keeps going, going, going. Even though they're getting closer and closer to that y-axis, they never really touch it. And this is how we're going to treat it. We're going to say, okay, we're going to look at the limit of -1 to t as t approaches 0 from the left of our integrand, plus the limit of t to 2 of our integrand as t approaches 0 from the right. So this is how we're going to evaluate this. It might diverge, it might converge, we're going to see, but this is how we have to evaluate it, because we have to recognize that we can't just skip over 0 because there's something pretty substantially important happening at x equals 0. So let's give ourselves a little bit more room here, and we'll evaluate these integrands if we can. So this equals the limit as t approaches 0 from the right, and just thinking through what the antiderivative of this is, it'll be an x to the -1/3, and then times a -3, evaluated from -1 to t. And we'll add this stuff also, but let's deal with this first and see if we can see what's going on. So if we plug in the limit as t approaches 0 from the right of -3 t to the -1/3 minus a -3 times 1 to the -1/3. Okay, this here is just 1 to any power is 1, so this all is just -3. That's no problem. So we'll have a -3, and then let's see if we can talk our way through this here. We have a -3 and t to the -1/3 power. This is like 1 over the cube root of t as t is approaching 0 from the right. Well, that is a problem, because then that creates a 0 in the denominator. So this part of the limit does not exist. This limit doesn't exist. And so this whole limit doesn't exist, which means that it doesn't matter what this is going to be. There's going to be problems in this one also. But as soon as we hit our first problem where the limit doesn't exist, the limit cannot exist for any of it. This limit does not exist, so we say that this integral is divergent. And that's the whole solution. It never converges to a number. It is possible to create an erroneous solution. Oops, I'm missing an S here. Erroneous solution. If it's not noticed that there's a vertical asymptote right smack dab in the middle of these limits of integration, you could say, oh, okay, the antiderivative is -3 x to the -1/3, evaluated at -1 and 2. This is equal to -3, 1 plus 2 to the -1/3. This is a real number, but this is not true. So we've kind of ignored in this solution this glaring vertical asymptote. We do have to deal with it like this, and it ends up that this integral is divergent. Last example we'll look at is the integral from 0 to 3 of 1 over the square root of 3 minus x dx. And so this too is a type 2 improper integral. Neither of the limits of integration is infinity or negative infinity, but if you tried to plug in 3 in for your x, you would have a 1 over 0, and so that indicates that there's probably a vertical asymptote going on. And in fact, if you graph the integrand, you'll get a not like that. Here's 3, the graph of it. There is in fact a vertical asymptote at 3. We're asking it, this integral is asking for us to find the area between 0 and 3, but this will never cross that line x equals 3. It keeps on going forever and ever, so we just have to determine, does this converge or does it diverge? So we'll go ahead and use our t, and we'll say the limit from 0 to t, and since we can't really touch x equals 3, that's not a continuous part of the integrand, but we're going to get closer and closer to it, as close as we can, of this. So t is approaching 3 from the left, and this is going to equal, once we do the integration, this is like a -1/2 power, and so we have a 3 minus x to the +1/2, and we would have a negative 2. Let's just double check this antiderivative. So we take this, multiply here, we'd have a negative 3 minus x to the negative 1/2, and then chain rule times another negative. That would cause everything to just become this. So, or this. Okay, so we do have the right antiderivative. Now we're looking at this expression evaluated from 0 to t as t is approaching 3 from the right. And this will be negative 2. Nope, gotta write the limit. T is approaching 3 from the right, and it's negative 2 times 3 minus t to the 1/2 minus a negative 2, 3 minus 0 to the 1/2. Okay, so this limit, we think through what this is going to mean. This part is just a constant. It's not dependent on t at all. It's just going to stay what it is. But as t gets closer and closer to 3 from the left, like think 2.9, 2.999, this becomes a very small number. And it's the square root of a very small number, but it just becomes smaller and smaller and smaller. This part of the expression goes to 0. And so this whole thing goes to 0. We're only left with this, which is 2 to the a positive 2 times 3 to the 1/2, or 2 times square root of 3. This is the area, the finite limit of this area here. This unbounded region is going to have a finite area. So just to summarize our first type of improper integral, this was one example where one of your limits of integration is infinity, or possibly both of them. This will either converge or diverge. You've got to figure out which one. And then this as well is where you have some kind of vertical asymptote right in the middle of your limits of integration for this function. And this too, you have to kind of split up and deal with and look at it as a limit. Both of these have to be thought of as a limit. We use a variable t as it approaches maybe infinity, or maybe it approaches, 3 from the left or 0 from the right. And we look and see what happens at those kind of exceptional spaces. So this is the idea of improper integrals.